All right, today we are talking about randomization tests, okay? So that's exciting, so I don't know. Okay, so first of all, we're gonna just start with a review of comparing proportions, okay? So, so here's a simple example, right? Is the proportion of international students different for stats majors and applied math majors? And so I'm just completely making these numbers up. I have no idea, okay? I haven't done any I haven't asked for any data on the thing, right? So anyway, let's say I get a random sample of 150 students majoring in statistics, and we find that 75 of them are international, okay? And then we get a random sample of 160 students majoring in applied math, and 64 of them are international, okay? So the question is, does this provide evidence that the proportion of international students is different for students majoring in statistics and students majoring in applied math? All right, what do you guys think? 75 out of 150 versus 64 out of 160. Is there a difference? Yes, no, maybe? Okay. Well, how would we... So if you think back to your days of Stats 10, Intro Stats, AP Stats, whenever you took your introductory stats class, what is the test that we would use? I want to compare the proportions of these two groups. A Z-test. Okay, great. All right. Or another option would be... T-test. Not a t-test. Chi-squared test. Okay, great. All right. So, thank you for not breaking my heart. Okay. Anyway, yeah, this is stuff you guys should know, right? Like, you guys are third years, you're going to be graduating next year, or some of you will graduate in 13 weeks here. Break my heart if you can't compare proportions, all right? Okay, so anyway, yes, we can do a Z-test. A Z-proportion test, we're comparing the proportions of two samples, and this is what we have in our data. Statistics, in that group, 75 are international out of 150 total, so our observed proportion is p hat stats, 75 divided by 150, we get a proportion of 0.5, okay? Applied math, 64 international, 160 students total. Our observed proportion would be 64 divided by 160, or a proportion of 0.4, okay? And the observed difference between the proportions is p hat stats minus p hat math. We have a difference of 0.1, right? P hat stats is 0.5, p hat math is 0.4. That difference, 0.5 minus 0.4 is 0.1, okay? So that's what we have in the data. And the question is this difference of 0.1, is that statistically significant or not, okay? I guess that's this part, this page, right? So when we set up our hypotheses, the null hypothesis, which always has an equal sign, would be something along the lines of both majors have the same proportion of international students. Or in other words, there is zero difference between the proportion of international students for the two majors. So we would say P stats, so the null hypothesis, which is always about the population proportions, we'd say P stats minus P math, that difference is 0, okay? And then the alternative hypothesis would be that there is a difference, right? That this difference is not 0. So we'd write P stats minus P math is not equal to 0, okay? With the not equal sign, how many sides are there to this test? 2. Not equal sign makes it a two-sided test, or what we might call a non-directional test, okay? And so so here the question is, if the null hypothesis were true, we would expect the difference between proportions to be 0, and what we observed was a difference of 0.1. And is that difference statistically significant? All right, so your gut feeling, what do you think? Yes? No? Maybe? All right, well, we'll do some math, right? So maybe you forgot the exact part of this, but this is what we have. The central limit theorem, we can, because of the central limit theorem, we can approximate the sampling distribution of a difference between sample proportions with a normal distribution, right? So we have the distribution of this quantity, p hat stats minus p hat math, comes from the normal. It's centered at 0 if the null hypothesis were true. And the standard error would be this quantity, square root of p hat times 1 minus p hat times 1 over n1 plus 1 over n2, right? So, and p hat is represented, in this case, is the combined proportion, y1 plus y2 divided by n1 plus n2. Okay. Is this all right? Maybe? Kind of familiar? Maybe it's been a little while, right? And so in our case, what we want to do is we want to calculate the p-value, and the interpretation of the p-value here is what is the probability that two populations with the same proportion of international students would produce two random samples where the difference is 0.1 or something more extreme, okay? And again, because our alternative has that not equal sign, we're interested in both a positive difference of positive 0.1, or we're also interested if the difference were negative 0.1 or something more negative. So, so we would put an absolute value around this quantity, p hat stats minus p hat math. We put that inside an absolute value signs, and we want to know what's the probability that the absolute value is greater than 1, or greater than 0.1, okay? And so we would be interested in either a positive or negative difference, and so this is how we would calculate the p-value. And so here's just some math, right? Or just some arithmetic. We're just plugging in some numbers and doing some computations. So we have y1 plus y2 divided by n1 plus n2. We get an overall proportion of around 45% international students in our sample. And then if we calculate the z statistic, we have p hat 1 minus p hat 2, 0.5 minus 0.4. Okay, in the numerator we have our observed difference of 0.1. Okay, and then when you plug in all of these numbers for the denominator, you get a standard error of around 0.05, and that corresponds to a z-score of around 1.77. Okay, so just a little shy of our, our baseline number of 2 or 1.96, right? So anyway, we do the calculation. The p-value is a probability that the absolute value is greater than 0.1, which translates to probability that z is greater than positive 1.769 plus the probability that z is less than negative 1.769, right? Because we're looking at both the positive tail and the negative tail. So we're interested in both of those things. So it just ends up being 2 times one of the tails of 0.0384. We get a p-value of around 7%, 0.0768. So something right around there. All right, that ends up our p-value. So our p-value is 0.0768. If we use a significance level of 5%, our p-value is larger than alpha, and we do not reject the null hypothesis. Okay, and the data that we have, we would say that the data we have does not provide evidence that the proportion of international students is different for stats majors and applied math majors. Okay, or in other words, if randomness is the only source of variation between samples, then it's still possible for two populations with the same proportion to still produce two random samples where that difference is 10%, which is what we observed. Okay, and that's going to happen with a probability of around 7%, 7 to 8%. Okay, and this is not a large probability, but it's not small enough for me to just completely dismiss it. Okay, so I'm not ready to say that this difference of 1%, or not 1%, of 0.1, 10%, we can't say that this difference was caused by something other than random chance. Okay, so as far as we go, all we can say is we're not ready to reject the null hypothesis. Perhaps there is a difference, but it's also quite possible for random chance to produce the difference we observed at 10%, 0.1. And so we can't conclude that there is a difference in the populations. All right. Is this okay? The logic behind this z proportion test, I'm hoping it feels at least familiar enough, okay, from your intro stats class back in the day. Okay. All right, so here here's a question. Let's see how much you remember. What are the assumptions or conditions that that I'm making, or the conditions that are necessary for me to do a Z proportion test? Yeah.
Independence.
Okay, independent. So meaning the two samples I select have to be independent of each other. So that's true. Or that the two samples we have were randomly selected or something. Okay, fair. What other assumptions am I making or conditions are necessary to use the Z proportion test? Yeah.
The sample size should be large.
Okay, sample size should be large. So what constitutes a large sample size for a Z proportion test? Yeah. 30 or greater. 30 or greater would apply for a t-test, okay? When you have a numeric response variable. So that's a good rule of thumb for numeric. But in our case, we have a categorical response, people who are international or not international. So we have a slightly different large sample size idea. Yeah.
Like n times p and n times 1 minus p have to be greater than 10.
Oh my goodness, you got it, right. So we need very good. We need at least 10 yeses and 10 nos, okay? The sample size needs to be at least big enough so you have at least 10 yes cases and 10 no cases, right? So another way is that n times p, which is your expected number of yes cases, has to be greater than 10, and the expected number of no cases, which would be n times 1 minus p, also has to be greater than 10, okay? So very good for remembering everything from your intro stats class, which is probably better than most. Last class, they struggled also. So yes, this is what we have, right? So we need, it runs on the central limit. Okay, so does anyone remember why the central limit theorem needs this 10 yes, n times p greater than 10, and n times 1 minus p has to be greater than 10? So what we have is a categorical variable of either yeses and nos, or international and not international, or something, okay? And so basically the count of who is, of how many international students you have in your sample, or the count of successes, follows a binomial distribution, okay? So you're gonna have 10 people who are 11 or 12 or something. You get a whole number, and the binomial distribution can be approximated with a normal distribution as long as your sample size is large enough. So as long as n is big enough, you can approximate the binomial with the normal distribution, and we say when n times p is greater than 10 and n times 1 minus p is greater than 10, that's when it looks like the binomial can be approximated with the normal distribution. So anyway, this is what we have. The samples that we had in our example were big enough. We had 150 students total for the statistics group, 75 yes cases, 75 international, 75 not international. The other one, we had 160 students and 64 were international, which means we had 64 yeses and 160 minus 64, 96 no's, okay? Or if we did the 0.5 and the 0.4 and the did our multiplications, everything would come back greater than 10, okay? If the conditions for the sample size are not met, then using the Z proportion test would give us the wrong p-value, okay? And could lead us to making the wrong conclusion. All right, and so in certain cases, you don't have enough data to run a Z proportion test, right? So in this example, we did like a random sample, and we asked a survey question. Are you an international student, yes or no? Okay, survey data in general is a lot cheaper to gather than experimental data, okay? So when you do a survey, it takes a little bit of time. You got to pay somebody to run a phone call, but they can probably call, I don't know, maybe 3 people an hour or something, okay? And you're paying the person $20 an hour or something. You know, maybe it's $7 per survey response, okay? So it's not free. I mean, I guess depending how complicated your questions are, right? I think if you try to do, okay, so first of all, don't ever do a survey via Google Forms, okay? I see sometimes people post surveys on the UCLA stats page or something on Facebook, and I'm always like, this is, how dare you? You are a stats student and you're gonna do a survey on the internet? There's no way this is a random sample. There's no way you're gonna get useful data out of the survey. So don't embarrass me by getting a job and then your boss says, oh, we need to do a survey, and then you say, well, let's do a Google form and I'll send this out to my contacts. No, don't do that, okay? You got to pay a survey institution, right? So Google actually will be able to conduct some surveys for you, and maybe you've done these on YouTube. Like you're gonna watch a YouTube video, and instead of a video advertisement, they say answer a survey question, right? That's Google making money off of your answering a question because somebody said we want to get some things, right? And so Google has a way of, like, they know exactly who you are, they know how old you are, what your preferences are, and so they say, oh, you're in the target demographic or whatever, and they want to get a survey of 18 to 24-year-olds who are whatever. Okay, so they ask you a question and you answer that, and somebody paid $1 to Google to get that click, okay? Or somewhere between 10 cents to $1 for each, just answering that one click, because Google has made some promises about it being a representative sample, right? Which is much better than a Google form that you're emailing to your friends.
Is that random or non-random?
It is, so they will, it's not purely random, but the premise that Google promises is that the people who go on YouTube is representative of whatever group that you're chasing after, which is probably reasonable because YouTube probably has close to 100% market penetration here, okay? And then, yeah, the computers then randomly pick who gets this survey question, right? And then they won't let you watch the, and I don't know, they figured out stuff. Okay, it's fairly representative is basically the point that they're making. And they charge basically close to $1 a response for each of these things, okay? But anyway, all to say, survey information, generally cheaper, but you might do an experiment, right? And we talked about how experiments are super expensive, okay? And so you might not have the luxury of having 10 yes cases and 10 no cases in your experimental data. Your experimental data, maybe you only have a few yeses and a few nos in your thing, okay? And so in that case, we might have to do a randomization test. A randomization test allows us to work around the central limit theorem, where we don't need to have 10 yeses and 10 nos in our samples, okay? So that's what we're going to cover. And for the example here, I've got a video, okay, from Mythbusters. I don't know if you guys remember the show Mythbusters. They used to do like these little engineering experiments and stuff. And anyway, this video used to be free, and then it's no longer free. I actually had to pay $1.99 for this episode, okay? So I have to stop recording this video because last time I recorded it and then I got a copyright strike against me. So